I'm Chris Sorrell, AI Advisory Practice Lead here at Catalyte. I'm joined by June Wang, our CTO, and Jason Foster, Principal Architect here in our Data Science group. And today we're going to talk about probabilistic versus deterministic systems. So when we talk about AI, we're introducing a new paradigm of uncertainty, and we call this probabilistic systems versus our traditional software engineering is about deterministic systems where we always know what the answer is going to be for a given input. And so we'll talk a little bit about how this applies to architecting for AI systems, how it applies to risk and cost, and how it applies to the way that we engineer our processes, our governance, and our policies. Thanks for joining me today, gentlemen. Today we're going to talk a little bit about probabilistic versus deterministic systems. Uncertainty equals risk in IoT systems, as we know. And of course, when we're talking about AI, we have a much larger scope of uncertainty. And I think it really does come down to that question of probabilistic versus deterministic systems. So we're going to look at that, unpack it a little bit, see what that means and how it applies. So I think maybe really the place to start with that is, what do we mean by a probabilistic system versus a deterministic? So June, maybe you want to start with that?
Cool. Yeah, it's a great topic to discuss. I think it's actually very relevant to these days. The generative AI is in modern technology. I think probabilistic versus deterministic. I think the example that I see other people use is like calculator as an example. If you type 1 + 1, it's always 2. If you type almost anything, it's the answer is guaranteed. Even if it's an error, it's like guaranteed error. And then these days, as probably a lot of people have experience with ChatGPT, even if you ask the same question, it'll give you different answers. And then Midjourneys or any of the sort of generational AI, generative AI, there's no guarantee you're going to get the same thing. Actually, it's almost guaranteed in some cases you won't get the same thing back. That's a problem in the generative AI for images and the videos. People want to get the same phase, make like AI generated video. So I think conceptually the difference between deterministic and probabilistic is like whether you get the same thing back, and the outcome of any sort of modern generative AI or more sophisticated technology is going to give you a probability distribution of answers. So instead of giving you an answer of 1 or 2, it'll give you maybe, 10% of giving you a 1, and then 50% of giving you a 2, and 40% give you a 3, and depending on a lot of factors, and sometimes it's completely random almost by design, you see a full distribution. So that's sort of the conceptual difference.
Oh, that's very interesting, and I like the idea. If you have an algorithm that adds 2 numbers and you supply 1 and 2, you're always going to get 3 in a deterministic system. It can't not be 3, and practically speaking, that's something that's easily testable. We have 100% confidence that it's going to be that, and so that code is written, and we don't have to care about it again. We know that part is handled. And so, we're in this new world now where that's no longer the case. And I think, why is it that there's this sort of distribution and this probable model that we're getting? Like, what's the difference here? Like, how's it coming to the conclusion that is it probabilistic instead of deterministic?
Well, I think there's a couple of things that are involved in that. I mean, if you're talking about prompts and questions that are asked, there's a lot of different ways. There's many, hundreds, thousands of ways to ask even a very simple question. And there's also a lot of things that you assume about your listener. Like if you're talking to a human, that they have their own biases, you have to sometimes communicate back and forth, and it's harder to do in these kinds of systems. Even for things that are more machine learning related, whereas some of those are maybe less probabilistic. Like if I give it these 5 variables, it's going to classify them roughly the same way. There's not a lot of bias that's built into those. So I think that there's definitely some issues in the way that you communicate what your questions are and what prompts you give it and how you want to ask them.
And just to be a little bit sort of on the details, technical side, especially as we go into the machine learning, going to AI, especially as the problem size get a lot bigger. effectively, like a lot of the AI is searching for optimizing for something, right? And for those of you who are familiar with like the gradient descent algorithm, it's basically trying to find a maximum or minimum solution of something, minimize error. And then it is mathematically been proven the best way or at least one of the best ways to approach it is to reset the starting point so that you can sort of search for different kind of a local maximum or local minimum, and then that is the sort of the origin of the randomness, the origin of the probability distribution. We need to sort of see the starting point of a search of a local maximum many different times in order to find the much better near global maximum or near global minimum. And in those cases, we introduced randomness in, and as a result, you see a probability distribution, because in a lot of real life examples, there's no right or wrong. There's no like absolutely best answer instead of like the calculator example. So we want to give you the most representative of distribution so that the users have full visibility into everything.
And even the models, when they're trained, they're not trained to be 100%. You're never going to get that kind of, they're not going to get that deterministic, that way of making those answers, because the models are the way that they're trained has that sort of error built into there. You can't ever get 100% like you can with a calculator.
And I think, when we talk especially about natural language processing, which is foundational to generative AI in a lot of ways, it's really concerned with inferring meaning or intent from language. Again, AI doesn't know anything. It just knows essentially numbers and the relationship between those numbers. And so when we say something like, what can I make as a carpenter? Do we mean what can I physically build as a carpenter, or do we mean what can I earn as a carpenter? And of course, we as people talking use our context clues to figure out what that means. And I think similarly, AI needs context to do that. But this goes back to these questions of percentages, right? And when we talk about that, I think we refer to them a lot as like confidence scores, right? And what it's saying is, I'm 90% confident that he means what can he build as a carpenter, and that's of course by context. But from a technical standpoint, and maybe you can talk about this a little bit, there's a lot of smaller confidence scores that go into building up to that ultimate one. That's is like a decision tree. Yeah, exactly.
Right? I think technically, I'll make a bolder statement to say like the probabilistic system is always better, if you don't worry about the cost, better than the deterministic system. Like imagine in the carpenter example, like we deterministically always answer like, I don't know, $50,000 a year or something. Then you lose the flexibility. Even if later on you learned, like, we're talking about what kind of furnitures you're making, then you lose that flexibility. So being able to build a distribution of probabilities is always going to give you the flexibility needed. Then later on, as you mentioned, you can use all the other sort of confidence score to build up, so that if you can tweak the probability distribution. Maybe starting with, I don't really know, randomly, I'm going to answer 50-50. But as I earn more context, as I become more aware of the conversations before, or the attribute that I learn about this particular person, then I can answer this as an AI sort of differently and give you a slightly different probability distribution. And then you can always sort of quote unquote collapse the probabilistic scores into deterministic scores by just giving one of the outcome 100% probability, and then just everything else collapse to zero. And that is always an option you have.
But a lot of those things are based on the corpus that all of that stuff comes from. So, and you're limited by the relationships between the words that are in the sentences inside the corpus. And so when you're talking about lacking context, it doesn't know 5 paragraphs ago that we were talking about something else, right? When you're talking as a human. The other side of that might be to take the conversations that that you had, the questions that you got, how they were corrected, what additional things were put in there. You can add those back into your corpus to have it become a little bit better and a little bit smarter about kind of what you think it means. Maybe the confidence scores for those things go up.
Exactly.
Oh, that's excellent. And so how do you think bias factors into this? Because in a totally unbiased system, you should have a true random distribution of probability. But bias is essentially going to shift that in some way, right? And so how does that work in terms of the training, and how do you mitigate for that?
Yeah, so I think, again, it goes back to what's the source of the corpus that you're using for those things. Because if you're going to train on things like Twitter or things like that, right? The language that is used in social media is much different than the language that's used in formal publications. It's much different than the language that's just kind of even used in business or even just in general email. So you have to kind of understand how to weight some of those things. You have to maybe sometimes build those things or expand those keywords when you see them, like IDK means this, and so I'm kind of putting things together, right? But you have to understand kind of where that data came from and how much can you really trust it. What bias is kind of built in there, right? Because on social media there's a lot of opinion, maybe not as much fact, right? In medical publications, those are peer reviewed. There's a lot more, you can sort of trust the facts that are, and you can trust the relationships between the words there, but maybe obviously a lot more than in social media. So I think it goes back to the corpus.
Yeah. I want to throw into just at least a clarification on my side is like when we talk about bias, at least from a purely technical standpoint, it's a neutral term. It's not necessarily good or bad. The bias just means the sample distribution is different from our sort of intended application distribution. If you have, let's say, like gender difference, or if you call it gender bias, right? If you're training Twitter as an example, like Twitter is probably like more male than female, and then you have a, let's say, I don't know, 40-70, 40-60 distribution, and when you're intending to use whatever is trained on your audience, and maybe it's a heavily female population, and that's a bias that we introduce, the bias between the sample bias and the application sample distribution and application distribution, and there are a variety of techniques that we can use to sort of compensate for that, or at least either by sampling or gather different data, or just tweak the weights a little bit. And sometimes in large language model is fine tuning. And in other sort of predictive analytics and other machine learning, there are a variety of different techniques that we can use to do that.
I think I love that concept of neutral bias being a neutral concept, and it is, if you think about like a race car, for example, most race cars have independent bias controls on each of the wheels for braking. And so what it's saying is you can adjust the braking force of each wheel to optimize the way it goes around the track, and so that they are essentially neutral. They're not good or bad. They're just, well, how do we weight this to ensure that we have the optimal result for the business case at hand or the problem at hand.
Exactly. And you have a goal that you're optimizing for.
Right. Exactly. Good. I want to maybe dive a little deeper into sort of this. We talked a little bit about inferring meaning. And when we talk about, I'll introduce the concept of vectors, and at a simplistic level of vector, when we talk about it, is really the sort of distance and direction between two words, right? When we think about it in at least vector databases. And so I'd like to maybe explore a little bit about what that means. If you think about something like the two words latex and paint, if they're completely independent words. How does AI know you're talking about latex paint versus latex gloves and oil paint? And so how does that work when you're getting into like vector databases and those systems?
I think generative AI, what it allows us is to basically map all the traditionally like big data kind of data, like text, images, and videos, and whatever else, into like a mathematical representation. And the vector database concept, or the embedding of the embedding concept, is to basically convert things that's not traditionally understood as data in terms of like numbers into a number, and like a number in a generic term in terms of like as a vector. So a standard implementation is you convert, like if we're talking about word embedding, and you can do sentence or paragraph or picture embedding, but word embedding is like every single word can be basically translated into, let's say, a 300 dimension vector, but it effectively means like 300 numbers. And then every word becomes 300 numbers, and then there's a lot of mathematics behind it to really make sure that they have meaning. But essentially, once you map all the words, again, or sentences or pictures into numbers, then you can calculate distances, like how much they are similar to each other, and so on and so forth. And you can do what you just said. Yeah.
So you end up with a multi-dimensional graph of the distances between words. And when we get back to the context question, latex paint, the terms latex paint mean nothing without context, but when you have that vector database, you can say, given the context of all the other terms that I was provided, the distance between latex and paint indicates it's most likely talking about actual latex paint, the product versus something else. And that goes into, I'm X confident that that's true.
Yeah, and again, like once you get in there, then you can do a lot of math. You can do conditional probability, like you said, like latex and paint are like the conditions for each other. Versus, I don't know, in mathematical formula, there's a latex that you can type in formulas. So the distance between those, like the vectors have a built-in distances between the two. But the more context you add, the more you can control the conditions, so that you have what we talked about earlier, the conditional, the confidence level, right? Then you can further improve your confidence level.
That's great. So maybe bringing it back up a level, as we kind of wrap up here, how do businesses handle this problem? All right, so we know we're in a world of probabilistic systems. You've asserted that they're fundamentally better, and I think that there's a strong argument that they are fundamentally better. But how do we handle that uncertainty so that we're maximizing the better instead of the risk there? Do you want to start with that?
Yeah, so I think, some of that, we talked about this before. I think the transparency of those things is crucial, right? To be able to understand where that confidence number came from, not to just have it be a black box, but to be able to, if someone digs, to be able to at least say, hey, this is kind of why we think that this is going to be right. It's based on X, Y, and Z. But I think it's hard to explain mathematics. It's hard to explain, exactly how you would come up with that calculation. But even just being transparent about the confidence level that you have and saying we're 90% or we're 80% or we're 60% confident that this is what you mean. You can also tell by the way that the person reacts to the answer that it gets, right? If it rephrases the question and rephrases it again, says no a lot or shows frustration or things like that. There's some feedback that you can kind of take into account. But I think ultimately that's part of it. That's a big part of it, is that transparency.
So how do we, are there, because we think about traditional software engineering, we have risk management typically handled through things like unit testing and other feedback mechanisms that are largely sort of pre-production or before you release. But in this case, we have to have sort of systems that are post-production, that are feedback mechanisms to handle that. So are there processes and procedures? Where's the industry going with that?
Yeah. This is where we'll go a little bit more beyond the modular or like unit level of implementation, because like unit test as an example, it's very deterministic. If it doesn't really do what you asserted it's going to do, then you fail the unit test. But now we're talking about probability distribution. So instead of writing one unit test to say this is going to do this, you probably need to do many of them and basically make an assertion that we expect 10% result this, 20% result this, 30% result this. And then it becomes statistics. So I'll correct a little bit when I say probabilistic. This system is better. Theoretically speaking, it's always better. But in business context, you have to consider the cost associated with it. Now, instead of one unit test, you need to write 100 of them, and that's not even the right way to do it. I think the whole concept of unit test in this case is going to be redesigned so that we can measure the probability distribution, and then how much is the statistically significant probability distribution deviation from what you expect. Like those are different challenges that we'll have to deal with in our overall like new AI oriented systems.
So it's almost like user acceptance testing, right? Where you kind of let it loose in the wild and let people interact with it, and you see if you're really getting what you want. Is the system being used in a way that my engineers thought it was going to be used? Is it used in the way that we tested it? And like our unit tests and even our integration tests. Once you give it over to people to let them go, that's where the rubber meets the road. And you have to be able to see, does it meet my expectations? Is it giving me the same things that I thought it was going to give? And do I still have to go back and tweak it? Do I have to give it additional data? Do we have to do some different math on it, right? Or different optimization on it to get it to do what we think we want it to do?
Yeah. Another way to look at it is synthetic data, right? Instead of or in addition to like the data that we sort of manually very well curated data, we can do synthetic data and then test it at much larger volume without having the user to suffer. Like the user acceptance testing in a live production environment, there is a cost associated with there as well. Yeah.
So I think to recap, we've moved away from deterministic systems where 1 plus 2 equals 3, and we always know that, into probabilistic systems where we have a distribution of potential responses, and we have to get comfortable with confidence. How comfortable are we with 90% confidence versus 60% confidence? How comfortable are we with 80% confidence, but it's wrong, right? And how do we handle all of those? And so, a big part of that becomes, in the pre-processing side of it, introducing bias, counterweight, other ways to sort of optimize for the best case. And then on the other side of it is feedback mechanisms and ways to, improve that through, identifying these we'll call them failures as they happen, and start to, fix for them. And then, fundamentally, probabilistic systems are a leap forward, but there's a cost associated with them, and we can't, there's not a guarantee that it's the right system for every scenario. Just because it introduces adaptability, flexibility, extensibility in a way that is far greater than traditional software engineering doesn't mean it's right for the use case. If you have a simple problem that's never going to change, there's no reason to introduce a probabilistic system.
Yeah.